Well, we're going to first solve it graphically. And the way we're going to do that is we're going to graph feasible regions based on the constraints. So the acreage constraint, if we had an axis that had steer acres on one side and tree acres on another, if we devoted all the acres to steer, we'd have 1,200 acres of steer. If we devoted it all to trees, we'd have 1,200 acres of trees. If you look at the graph of the answer, here's the land constraint. It goes from 1,200 tree acres to 1,200 steer acres, and anything below that line is feasible. Next constraint is the year one cost. If we devoted our entire year one budget to steer, we would figure out how many steer acres that would be by dividing 142,500 by 75. And if we divided if we allocated our entire year one budget to trees, we could figure out how many tree acres we could do by dividing 142,500 by 150. If we look at our graph, here's our capital constraint. So if we devote all of our year one capital to trees, looks like about 950 or so acres of trees, 1,900 acres of cattle would use up all of our money. And if we draw a line between those points, then that line is the combination of tree acres and steer acres that uses up all of our capital. And anything below that line, which is what this arrow means, would be feasible. And we have one more constraint. The erosion constraint, we would say if we devoted all of our erosion budget to managing for steer, how many acres could we have? And that looks like it'd be 1,000 acres. And if we devoted all of our acres to trees, how much erosion could we afford? And it looks like that would be maybe 2,000. And there's the 2,000 erosion constraint on trees. There's the 1,000 erosion constraint for cattle. So any combination on that line would use all of our erosion constraint. Anything below that line is feasible. So what we've got so far is the area that would meet this constraint, and then it has the feasible region, which would meet all three constraints, is going to be below all these three lines, which would be this area from here to here, here to here, and here to here. So that would be the feasible region we would shade in if I was going to shade in the feasible region. You may look at this and say, okay, what's the answer going to be? It's got to be at a corner, and that's really all we know. Until we put this benefit line on it, we don't know which one of those corners is the one that maximizes our benefit. So for example, if we had a very high value on steer, so it only takes a few steer to be worth $100,000, but a lot of trees to be worth that, that'd be a vertical line. The highest benefit you could attain that still would be feasible looks like it would be all steers. So how do we graph the benefit? We choose an arbitrary benefit level, and on the next page there I chose 900,000 because it was an easy thing to figure out with these two SEVs. So if we want to figure out how many tree acres would it take to be worth $900,000, it's going to take 1,000 acres of trees and 900 acres of steer. Hopefully that's what it shows over here. It takes 900 acres of steer and 1,000 acres of trees. And if we take this line out and parallel, the point it would hit would be that corner there. If we were doing this with our own graph and wanted to verify it, we could always say, okay, it's either this point or this point, and we could figure out the value of this point and this point. If I ask you to figure out exactly what the answer would be using the graph, then the way I would do it is, from the graph I can see that there's two binding constraints. The binding means that the answer is sitting on that line and we're using up all of that constraint. So we are using all of our land on this constraint, and we're using our total erosion budget. So if I went back to this problem, I could look at the erosion constraint and the acreage constraint. I know that the answer is sitting on both of those lines, so I could convert these to equal to, and I could say that 1 times steer acres plus 1 times tree acres equals 1200, which means that steer acres would be equal to 1200 minus tree acres. I could plug that into the equation for erosion, which is 0.2 times steer acres plus 0.1 times tree acres equals 200 because it's sitting on the line. So that gives us the 2 equations and 2 unknowns which we could solve for, and what it should tell us is that 400 trees and tree acres and 800 steer acres is the optimal solution. Here's the same problem just set up as an equation. So our objective function is 1000 s plus 900 t, which would add up to total SEV, s meaning steer acres, t meaning tree acres. 1s plus 1t has to be less than or equal to 1200. 75s plus 150t has to be less than or equal to 142,500. 0.2s plus 0.1t is less than or equal to 200. So those are the coefficients that we extracted to make our detached coefficient matrix. And an answer to an LP problem has 2 parts. One is, what is the optimal allocation? And the next is, what was the value of the objective function from that allocation? So if I ask for the answer to this problem, the answer is not 1,160,000. That's an incomplete answer. The answer is an allocation of 800 acres to steer, 400 acres to trees, which leads to an objective function value of $1,160,000. So that's the way to set it up graphically. We can go through some terminology here. If I ask you which of these constraints are binding, we use that to solve for the answer. So the land constraint and the erosion constraint are binding, which means they have no slack. The capital constraint is not binding. In other words, the answer is below that line, and anything we could have spent more money. If we wanted to figure out how much slack there was on that non-binding constraint, what we could do is take the 800S 400T answer, plug it into the cost constraint. So 75 times 800 acres of steer plus 150 times 400 acres of trees is going to be some amount of money that's less than 142,500. I think it's 120,000. The difference between the right-hand side and what that adds up to would be the slack. Another thing to note is linear programming requires the equal sign because the way it works is looking for corners. Well, the corners are made up of lines, and if you didn't have less than or equal to, the line would not be part of the feasible region. So that's why the equal sign has to be there. Another term to bring up is the shadow price. And the shadow price is how much the objective function would change if you added 1 to the right-hand side of a constraint. And I believe the shadow price on this problem for the land constraint, which is binding, is 800, which means that if we solve this problem all over again with 1,201 acres rather than 1,200 acres, the answer we would get would be 1,160,800. Why that's interesting is we know which constraints and which constraints are not binding, but we don't really have an idea of how important that binding constraint is. By looking at the shadow prices, you could say that if I had 1 more acre, my total SEV would go up by $800. If I could buy land for less than $800, then I could increase my net revenues because I know that when I buy an acre, my SEV goes up by $800. So big problems, you're not just looking for an answer, you're trying to get an idea of what's important in this problem, and the shadow price is an easy way to find out which are the important constraints. For this non-binding constraint, the shadow price would mean how much would my objective function value go up if I had $142,501 to spend? Well, we didn't spend all of our money in the first place. So the shadow price of non-binding constraints is 0, but non-binding constraints have a slack, a non-zero slack. Binding constraints have 0 slack, but they have a non-zero shadow price.